So, from the double slit experiment that was discussed in the previous video, along with information from the photoelectric effect that we talked about towards the beginning of this chapter, Louis de Broglie was able to derive an equation that stated that related that all matter has a characteristic wavelength. You just may not be able to see it based upon its properties. He was able to express that relationship in this equation that the wavelength associated with a particular piece of matter is equal to Planck's constant divided by its mass in kilograms multiplied by its velocity in meters per second. So I will give you, you're welcome, another equation that I will give you for your exam. You just need to be able to use it appropriately when calculating wavelength associated with a particular piece of matter. So in lecture, we will do question 2 as an example. Let's do this first question as a way to practice calculating wavelength associated with particular matter. Specifically, I want to know what the wavelength of an electron is that is moving with a particular speed, and I have the particular mass of the electron, and I gratefully gave it to you in kilograms. So I can use that mass along with the speed and Planck's constant to calculate the wavelength associated with that species. And you may think, wait a minute, the seconds are going to cancel, but how's the joules going to cancel out? Well, remembering that a joule is a kilogram meter squared per second squared, I know that my joule is going to cancel with the kilogram, with one of the meters and one of the seconds. And so I'm going to be left in the numerator with meters per, well, I'm going to be left in the numerator with just meters. So the wavelength associated with that electron is going to be 1.22 times 10 to the negative 10 meters, or 0.122 nanometers. So it's kind of weird to think that all matter has wave-like properties. You just may not be able to see it with your particular with naked eye. We will do another example in class with what the wavelength is for a particular person. But let's end this video with a conversation about implications of this wave-particle duality. The fact that we can think of mass, or we can think of electrons as particles and as waves. That leads to the uncertainty principle, the derivation of which we're not going to talk about in this class. So you do not need to know this particular equation, you just need to know the implications of it, which is that because electrons have wave-like properties and have particle-like properties, there is some uncertainty as to where an electron is in an atom. We cannot simultaneously, with the same level of accuracy, know the position and the speed of an electron both simultaneously with both the same level of accuracy. That is the definition of the uncertainty principle, and that is a hallmark of Schrodinger's equation, which speaks to calculate within levels of probability where an electron is in an atom. We're going to talk about those calculations and those equations in a little detail in the next video. But from this video, you should just know the uncertainty principle. You cannot know simultaneously the position and speed of an electron at the same time.